In this video, we're going to look at the calculation of the marginal distribution and how it's useful to assess the appropriateness of the prior distribution. I think we sort of touched on this before. So remember that we have the distribution of x given theta, and then we have theta, which follows some prior distribution, so our prior density. And then to get the joint density, which we typically label as H in this textbook, we multiply the prior density times the conditional density of x given theta. And the book uses the notation m of x given pi to emphasize that this is the marginal on x, assuming the prior distribution that we did. And obviously that will change if we use a different prior. To get the marginal density of x, we integrate the joint distribution. So you can see here that we're integrating out theta, so we're integrating over the parameter space. And recall this notation with d sub capital F, which we've looked at before. And so if we expand that, so if we write that in a more common way, assuming that we have a prior density, then we get this for the continuous case and this for the discrete case. Now at this point, we're going to look at the marginal distribution to assess whether our prior distribution is appropriate. And the marginal here, this distribution here, is sometimes called the predictive distribution, because if our prior is appropriate, then this really is the density which governs the random variable x, and it's free from theta. All right, let's look at this example. This is example 10 in the notes, but this is actually in our textbook in this section. So we're going to assume that we have x given theta is a normal distribution with mean theta and variance sigma sub f squared. Now here theta is the only unknown. These other parameters are assumed to be known. And so we're going to also take the prior distribution to be normal with mean mu sub pi and variance sigma sub pi squared. Again, both assumed to be known. And what we want to do is go through the steps to show that the marginal distribution turns out to be normal as well with the parameters you see there. So for the solution, we first want to write out the density of x given theta, which we typically denote with an f. And then the prior distribution is that normal as indicated earlier. And now we need to multiply these two, and that'll give us the joint distribution according to that formula, as we see there. And then doing a little algebra to combine things, we get this. And then now, looking ahead and knowing that we're going to have to take this joint distribution and integrate out theta, our next step is going to be to write this as one fraction and then complete the square in theta. You can see that I've first chosen to write this as one fraction and then also multiply out those binomial squareds. And then now let's just focus on the numerator and try to identify this as a quadratic in terms of theta. And then to simplify things, we're going to refer to the coefficient of theta squared as little a, and then similarly this we're going to refer to as little b and little c. And note here that each one of these is either constant or a function of x. So in terms of theta, later on whenever we do our integration, in terms of theta, those are constant essentially. So then we have a theta squared minus 2b theta plus c, and then, just do the steps to complete the square, and what we get is what we see here. And notice that I've also defined this d here, and I think this is called xi. I'm going to call it squiggly. So we've defined these two additional constants, and still none of these constants, I'm going to call them, that we've defined depend on theta. So in terms of, as far as theta is concerned, they are constant. Earlier, I tacitly just broke off and looked at this one particular part that's written in green here. But now it's time to put all this back together. So what I referred to as star here, we're going to continue with down here. And so here is our joint density, and this is what we need to integrate in order to get the marginal for x. So remember that theta, the prior for theta was normal, so it's concentrated on the whole real line. So we've got to integrate over the whole real line, as you see there. The next thing that I did was I separated out this constant part involving the d, which I put there. And then you notice that this is similar to a normal distribution. And so it's similar to what you see there. The mean would be b over a, and the variance would be squiggly times a to the negative 1. So then that tells us what this integral is. It's what we have written right there. And you can tell that just by your knowledge of what the normal PDF looks like. So now we need to simplify this and try to decipher what we have here. And what that is equal to is what you see here. But there's a lot between those two equal signs. So the first thing is to focus on this d over squiggly, which I've made note of over here. And it does take a good bit of algebra once you go back and refer back to what the constants were defined as, and then now you've got to put it all back together. And if you want to see where I did that, it's here. But again, all of this, I encourage you to do it all yourself with pencil and paper. And then once you get to this here, then you recognize that as the normal distribution that was referred to in the problem, what you see here. The reason why we are interested in the marginal distribution is because we can use it to investigate the feasibility of the prior distribution that we chose. I alluded to this earlier, but the marginal is called the predictive distribution for x because if our prior distribution was aptly chosen, then the marginal distribution should be what predicts the values of the random variable x. And so if we had observations from our data and the marginal distribution that we got is a distribution for which the values that were observed are not very likely, then that is a signal that something is wrong. And in future videos, we will investigate ways that the marginal distribution can be used in our selection of a prior distribution.